Okay, so we are in this book here, Generalized Linear Models with Examples in R. We're in Chapter 2, and we are on question 2.7. Okay, so we want to show that the variance-covariance matrix of our estimate for beta hat, is equal to this expression here. Okay, and during that, we're going to end up using a property of variances where if you have a constant c, and c can be a scalar or a matrix, then the variance of the constant times your variable, you bring the constant out front and behind as a transpose. If it's not a matrix, then it just becomes c squared times the variance of y. Okay. So let's kind of get going with that. So we have our familiar expression for beta hat, which is given here, and then I'm going to replace y with our expression for y, which is x beta plus epsilon. Okay? And so now if I distribute the x beta and the epsilon to the rest of the matrix, or the rest of the expression, then I get this term, right? So this is the thing that's common for both, plus, well, actually, this is the thing that's common for both, and then here's the x beta, and then here's the thing that's common for both times the epsilon. Okay. So you'll notice then that in this expression here, if I go from here and I drag all the way to here, so excluding that little beta, I have this thing, which is a matrix, and I have it again, but I have its inverse. Okay. And so it being a I can't remember what the term is called, but when I have the inverse times the matrix itself, it just becomes the identity matrix, which is just like multiplying by 1. So now I have the identity matrix times beta plus what was left of the other term. And so then that just gives me all of this right here. So that's an expression for beta hat. And now I want to find the variance for beta hat. So I need the variance of this expression, right, which is right here. Okay. And I can break that down into the variance for beta plus the variance of this other term. Well, beta, this not being our estimate, this being an actual value out there in the world, this is a constant. So beta itself has no variance. Beta hat does, our estimate does, but beta itself has no variance. Okay, so the variance of beta is just 0, and now we're just left with this term right here. Okay, so now we have this. Okay. Well, now using the property of matrices or of variance given to us in the question. Okay, then we have this big matrix here, and that's going to be like our C, right? That's going to be our C. Okay, and so I take this as the C, and then what I have left is the variance of epsilon. Okay, and then our C matrix again transposed. So all of that transposed. Okay, so that's using the property given in the question. Okay. All right. So now the variance of epsilon is given by a scalar sigma squared times what is the covariance matrix, which is our weighting matrix here, or the inverse of our weighting matrix. Okay. So now I can substitute that term in everywhere where I had variance of epsilon, right? So I have the same thing with variance of epsilon here. Okay, and then I'm going to fix up this last set of transposes here. Okay, or I should say this set of transposes. So the first thing I do, I need to flip the order of these. So first I'm going to take the transpose of this, and then the transpose of this. This is just a property of transposes. Okay, and so then I get to here. Okay, so now again applying that same thing here to get the transpose of x transpose w. I just flip them and take the transpose of each. So then I get the transpose of w is wt. And then the transpose of x transposes just goes back to x. Okay. And now for the second term here, the transpose of an inverse is equal to the inverse of the transpose. Okay, so I get this guy. All right. And then I can just take that transpose inside again, just like I did previously. And so now I'll have the transpose, I'll have to reverse the order of these matrices, and then take the transpose of each. So first I'll have the transpose of this x, then the transpose of this w, and then the transpose of this x transpose. And that brings me to this. And then I'm carrying that inverse right there. Okay? So we're getting pretty close. Now the scalar, or I'm sorry, sigma squared is just a scalar value. And when I have a bunch of matrices like this, I can kind of move those the scalars anywhere I want. So I'm going to take this scalar and put it out front of everything, and that leaves me with this expression. Okay, and then so you'll notice this W inverse here in the middle. Well, W inverse is equal to the identity matrix, right? So I get this, and I can just ignore the identity matrix because it's just saying whatever you've multiplied by it, you just get whatever the thing is that you multiplied by. Okay, so now I've simplified everything to this, and already the solution might be apparent, but I'm just going to move some parentheses to make it more obvious. So I'm going to take this parentheses, and I'm just going to put it here. And in linear algebra, we can put the parentheses wherever we want, more or less. So, so now all of that. Oh, I should have. That I can be there. I should have deleted it. In fact, I'm going to delete it right now before I forget. Okay. So now I've moved those parentheses. Okay. And so now you'll notice that I have this matrix duplicated. Okay. And one of the times it's an inverse. And so again, a matrix times its inverse is just the identity matrix. And so I'm left with this, and again, I can ignore the identity matrix, and so I'm left with that, which is what we wanted to find in the first place. Oh, and also in the question, the sigma squared is given afterwards, and the way that I've done it, it just happened to be out front. But again, with these scalars, which sigma squared is, you can kind of move them wherever. It doesn't make a difference. Okay, that's it.